In many applications, we don't know the joint distribution of more than one or two samples of stochastic process. Even sometimes we don't know the distribution. However, we need to process these random processes. So in many cases, just the expected value or cross correlation of the involved random variables are defined. In those cases, we describe stochastic processes using second order statistics. So this is why we define the mean of a random process. The mean of a random process is just to take a sample at time t. So this is just a random variable. If you fix time, time is fixed. If time is fixed, this is a random variable. Its expected value, we call it the mean of the random process. So this is called the first order statistic. Or the mean. Another definition is that sometimes you want to take two samples. This is time t1. Take time at time t1, another time at t2. So you get one random variable from this sample, and you get another random variable at this one. And then you want to calculate the cross correlation between these two random variables. We call it autocorrelation because it is correlation of these sample from this random process with itself. So the auto goes to self, but from two different time instances. So we take two time samples, and then we have two random variables and the autocorrelation function. We denote it by R, autocorrelation, XX. This means that this random process is taken a sample at this time t, and this one is also taken a sample this one. So X sample at time t1 is xt1, and this the second X at time t2. So the expected value of the product of them. So basically, this is nothing more than the inner product of X of t1 and X of t2. Remember that if you are dealing with complex stochastic processes, we put a complex conjugate on the second one. If we are dealing with vector random processes, we also put a transpose on here, and then the complex conjugate and transpose together, sometimes we denote it by by Hermitian. So in MATLAB, you denote it by just a prime on your random. For instance, if you put A prime, it is equal to both conjugation and transposition in MATLAB or Python or most of the programming languages. And obviously, when you want to calculate the expected value of product of two random variables, you need to have the joint distribution of two random variables. So the values that this guy takes on is x1. The values that the second one is taking, the value that the second one is taking x2, and then the joint distribution of these two random variables. So these two random variables is xt1, xt2, the joint PDF of them, and then you integrate them. So anytime you want to calculate the expected value of something, the value that this something takes on, which is this one, and the distribution of these entities. So the joint distribution of this one comes here. And because we have two random variables, we need to perform two integrals. Remember that one of the integrals is with respect to x1, and the second one is with respect to x2. So this is autocorrelation. Autocovariance, the only difference is that first you centralize this one, so that means that you take two samples at time xt1. You remove its mean, which minus mu x of t1, and then you take the second sample xt2 minus mu x t2, and then you multiply them together and take expected value. So this is going to be the autocovariance. Remember that if this random process is complex, you need to put a conjugate. If not, we don't need to put it. And then we call this one, we denote this one as autocovariance, covariance of x t1 at time t2. The only difference between these two definitions is that the second one, the random process is centralized, and then the product or calculate. So the autocovariance and autocorrelation. So this is correlation is because we don't centralize them. And autocovariance means that you centralize. So the covariance is because this is addition. If mu x t1 is equal to mu x t2 and is equal to 0, then these two functions are equal. If not, they are different. So obviously you could multiply these two terms by these two terms, you get 4 terms and simplify it, and you could see that this is equal to this one and then multiply. So this is the same thing that you had for any two random variables. So this is the second order statistics. These two are referred to as the second order together. If you are the mean plus this one is referred to second order statistics. This alone is the first order statistics. The whole thing, the three things, is second order statistic. So cross correlation of two random processes is that you take one sample from x of t at time t1, and then from x y of t you take a sample at time t2, and then you calculate their product. Remember that these x at time t1, these y at time t2. The second one at time t2, and then this guy gives you this one, and the second one gives you this one, and I calculate. So this will become cross correlation. And cross covariance, the difference between cross correlation and covariance is that this one needs to be centralized. Its mean should be first deducted. This should be deducted. So this becomes x of t1 minus mu x, the mean of a random process at time t1, and then y of t2 minus mu y at time t2. You multiply them together, and expected value is going to give you the cross correlation. Remember, if these are complex, you put a conjugate on the second one. Obviously, this expectation for this expectation, this becomes double integral of blah 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 that you know. So the cross-correlation coefficient, the difference between this one and cross-correlation coefficient is that this cross-coefficient is a normalization of this one. So is equal to the same thing, Cxy of t1, t2. It's like you have two random variables. One of the random variables is x at time t1. The second random variable is y at time t2. It's like a correlation coefficient of these two random variables. And divided by Cx x at time t1 and t1, and then Cyy of t2 and t2, but 1 square root over that. So this rho xy is always between between minus 1 and 1. So if it is complex, always its magnitude is smaller than 1. So for all t1 and t2. So this is called correlation coefficient between these two random variables, or correlation coefficient of these two random processes. Remember that this is a function of t1, t2, this is a function of t1, t2, etc. So all these second order statistics, they are 2D functions of time. For example, if I have two random processes, if I take a sample from the first one at time t1 and the second sample at time t2, calculate this one, I could expand this one. So I get x of t1 to the power of 2 plus y of t2 to the power of 2 plus 2y x of t1 and then y of t2. Now, if I put expected value, I will see that this will become rx x of t1 and t1. This one becomes ry y of t2 and t2, and plus twice rxy of t1 and t2. So we see that these statistics can be calculated using second order statistics of these two random processes.